Welcome to the course on design of power electronic converters. We were in the module of power semiconductor devices and we had started discussing IGBTs. So, last lecture I had started discussing some of the datasheet notations and some of the performance curves which are given in the datasheets of IGBTs. Now, let us continue discussing further of the datasheet of IGBTs. So, one important term that is given in your data sheet is your SOA or safe operating area. This while discussing MOSFET also I had taken it up. Now, it is also applicable for IGBTs. So, let us look into it, what is the origin of it. So, this shows your turn on process, and during turn on what happens is that first there is a delay and then after that the current increases, and at that time the voltage, the collector to emitter voltage is not changing much. So, if we plot a graph between your this collector to emitter voltage and collector current, then what will happen is that your this voltage remaining same, this current is going to increase, and then after that what happens is that this collector to emitter voltage decreases and the collector current is still high. So, that is what we see here, the collector current remaining high, your this collector to emitter voltage decreases. Similarly, during turn off, so this is for your turn off. So, during your turn off what is going to happen is that first the current does not change, but it is the voltage which builds up. So, current is not changing, it is the voltage which is first building up, and then the current decreases and the voltage remains close to the blocking voltage, and that is what we observed, that the current is decreasing here. So, what we see here is that this trajectory has to be inside a particular area for safe operation. So, that is your safe operating area, otherwise the device may get damaged. So, then for your MOSFETs what we had seen was that we saw only one SOA diagram, but for your IGBTs there are different SOA diagrams which are provided. So, first one is your simple one, SOA for turn on and single pulse operation. That means while the IGBT is conducting, what is the area inside which the device should operate, the voltage and current limits, what it should be within which the IGBT should operate while it is conducting. Okay, that means your turn on or during the pulse you have applied. So, that is the simple SOA operation. And then there is another one which is called as your RBFSOA, reversed biased SOA for periodic turn off. Now, reverse biased SOA, it is basically associated with the turn off process of the IGBT. So, while the IGBT is turning off, the time duration is very small, because the turn off time is usually small as compared to while it is conducting and the device is operating. So, then there are certain different limits that are there during that. So, it is called as reverse bias SOA, and to distinguish this SOA which is for your normal operation, this is also sometimes called as the forward biased SOA, FBSOA. Then there is another one in your IGBTs which is called as the short circuit SOA, SCSOA. This is let us say the IGBT has to withstand a short circuit. There is some short circuit, and that may be short circuit may be for a very small time duration, and the device might have to carry huge amounts of current during that time, and that means the device is conducting and the voltage across it also might be very small, and this is something that is going to happen once in a while, not going to happen periodically, as compared to your turn off process, which is going to happen periodically. Okay, so this is a short circuit is something a non-periodic phenomena. So during that also, since IGBTs has some short circuit withstanding ability, so during that also there can be some limits defined, which is your short circuit SOA, which is also sometimes provided in some of the data sheets for some IGBTs. So that is your short circuit SOA. So 3 of them, FBSOA, forward biased SOA, then reverse biased SOA, and your short circuit SOA. These are different types of SOAs for your IGBTs. So now let us look into this normal SOA or the FBSOA. So what you see here, there is first one limit, this is like a line with a slope, and at this point of time the voltage the collector emitter voltage is small. So this is basically the limits defined by the saturation region, whatever is the limit. Now do not think that this is 1 ampere of current that is going to flow. This is given as a ratio with respect to your maximum pulse current that can flow, and this also here is given as a ratio with your blocking voltage. So then after that what happens is that so this is one first given by the on state operation or saturation operation of the IGBT. Then there is this one, which is your basically your current limit. So this is your current limit. And then there is this one, which is your voltage limit. And in some of the data sheets you will also see this kind of a slopy line, which is not given here because this is taken from semicron, and they are not giving the linear operation limit because your power dissipation limit is basically when it goes into the active region or it is operating in the linear mode. So your power dissipation is basically your this voltage VCE multiplied by this current IC PD, your VCE into your IC. So how much this maximum can be, that there is a limit on it. So depending on that you can get this line. So that is contributed by your maximum PD. And further, in some of the data sheets people also give secondary breakdown. There is a phenomena called a secondary breakdown that happens in IGBT. So those limits also may be there in your SOA this diagram, SOA curve. All these limits are there, the current limit, voltage limit, power dissipation limits, and the first limit because of your during saturation what are the currents and voltage limits when the voltage is very small at that time, and secondary breakdown limit. So these are usually the limits in your FBSOA or the simple SOA diagram. Then let us look into your turn off safe operating area, which is basically your RBFSOA. So here this is you can see this is given as twice of IC norm. IC norm is this is your nominal current, Now usually what happens is that IGBTs or all these powered semiconductor devices, there is not just one chip inside the IGBT. It may be several of small chips that may be there, which may be connected in parallel, and then that may form one one device, which is what you obtain from the outside as the case, and the ratings are corresponding to that one device, where actually you may be having several of small chips that may be connected in parallel. So nominal rating is basically whatever each chip is capable of carrying current multiplied by the number of chips. Okay. So, so then this is usually the ratings are close to your IC, the continuous DC current rating. And so during turn off, some of the manufacturers give it as the limit as this your twice of this IC nominal. So twice of that is what during turn off the current the device can withstand at that time. And so this is your basically this one is your current limit. And here what you see is your this one is your voltage limit. Now here what you observe is this di by dt's are given. Now in an IGBT, what will happen is that let us say this is your IGBT. So, there may be some stray inductances also that may be associated. So, during turn off, as the currents are changing through these ones, so then there is an associated di by dt, whatever is the rate of change that is going to affect what is the voltage that is going to appear across it, and so finally whatever is the voltage the device might have to withstand. Okay. So, that affects basically the turn off process, and so your di by dt limits that are also they also reduce, you can see that this SOA the RBFSOA area. You can see here that this line is corresponding to 1 kilo ampere per microsecond, and as this di by dt increases, it increases to 5 kilo ampere per microsecond. You can see that this this SOA is reducing. Now we do not see any of these slopey lines here, which was because of their power dissipation limit, because it is only for the turn off for very small period of while the device is turning off, and so therefore those linear region limitations are not applicable in case of RBFSOA, and so they are not present in your RBFSOA diagrams that you see. Similarly, you can also see your short circuit SOA. The difference will be that these voltages that you see here, collector to emitter voltage, this will be much smaller, because much smaller voltage should be there across the device at the time, and the current that this can carry during for that very short time period for short circuit, that may be very high. Then further there may be notations related to antiparallel diode. This I had told you that most of the IGBTs the manufacturers make, they come with a additional antiparallel diode. So, this is that antiparallel diode, and so the characteristics of this diode will also be provided. So, your forward current IF, this forward current IF, what could be the maximum rating of that, then the pulse rating, diode maximum forward current for short duration IFM, this is your continuous current, and forward voltage drop, what could be the forward voltage drop across it, then reverse recovery time and reverse recovery charge QRR, these are also usually provided in the IGBT's data sheet. Now, one thing that I wanted to mention here is that you have got an IGBT plus you have got an antiparallel diode. So, you will need to do the loss calculations when you want to calculate the efficiency or you want to do the thermal design of your converter. So, at that time you have to calculate all these your switching losses and conduction losses of the IGBT as well as the diode. Now, usually there are too many calculations because all these are different voltages and currents all are varying. So, many times approximate calculations are done. So, then we should know which of these losses are dominating. So, for that this is a graph that is taken from Semicron's application manual, and here this is given for 1700 volt IGBT, 1200 volt is applied on it, and 150 ampere IGBT, and the diode it has got an antiparallel diode as well with it. So, this shows the IGBT turn on, and you can see that this voltage is reducing, and here this is your current which is increasing, and this is the power curve, which is your basically your P multiplied by your I. So, you can see here this area under this curve, under this power curve is your turn on loss E on, and then this shows your diode turn off. Okay. Earlier we had discussed this, that your turn on of the IGBT is going to be associated with turn off of the diode. Okay. So, this is your diode turning off. So, this is your voltage, you can see that it is building, and it is going to minus 1200 volt, and it was carrying this 150 amperes of current, and then further it decreases. This is the reverse recovery current, and then you also observe this tail current during the turn off, and then it finally settles to the leakage current. So, this is the power curve, which is P multiplied by P, which is equal to V into I. So, this is that curve, and the area under this curve is your this diode turn off loss ERR. And what we observe here is that this is much smaller as compared to this turn on loss of the IGBT. Turn off loss of the diode, you can compare here and see that this is much smaller as compared to the turn on loss of the IGBT. So, that is why many times people ignore the diode losses and only take into account the IGBT losses. Now, let us look into the thermal specification. So, R theta JC, which is junction to case resistance. Now, what is the junction in the case is all we have discussed before in diodes as well as in MOSFETs, and it is the same thing that is specified here as well, junction to case resistance. Then R theta CS, case to sink resistance, then R theta JA, junction to ambient resistance, then PD, maximum power dissipation, this also will be provided, junction temperature, what could be the maximum junction temperature, and TSTG, which is your basically your storage temperature for the device. Then another important curve that may be provided is your this collector current IC versus your case temperature, and as we expect, as the temperature increases, the collector current, maximum collector current allowed is going to decrease, and that is what we observe here, that there is a derating in the collector current. So, what are the key points of this lecture? One of the important curves in the data sheets is your SOA, safe operating area, and unlike MOSFET, your IGBT has different types of SOA. One is your normal SOA, or which is also called as FBSOA, and another one is only during turn off, which is RBFSOA, reverse bias SOA, and sometimes your short circuit SOA may also be given. Then antiparallel diodes turn off characteristics, that is important to look for in the IGBT data sheet if it has got an antiparallel diode with it. Then junction temperature and thermal resistance, these are associated with your thermal characteristics of the device, and there may be different performance curves that also may be provided in the data sheet which you can look for. Thank you.